Next, we will discuss the first convergence test that is called the integral test. And let's consider the following series. So this series can be written out like this. So it's 1 plus 1/4. It's just the reciprocals of squares of natural numbers. And the question is whether this converges or diverges. And let's try to visualize this series. So to do so, we are going to introduce a function, a continuous function, on which the sequence of terms resides. And we're going to look at this function to the right of 1. So what does it look like? Well, we can graph it. So it's a simple rational function, and it's decreasing, and it approaches the x-axis as x goes to infinity. And however, this is not the series yet. This is just a function on which the sequence resides. So what we want to do next is we want to look, again, we're trying to visualize this series, and let's consider, I guess, where is the series on this picture? And the series on this picture, it's not a trivial observation, but the series on this picture can be viewed as this area that I'm gonna show in green. So again, the scale, the vertical scale is a little different here. So let's say this is our 1, and then this area of this green bar will be equal to what? It will be the base times height, which is 1, and the area of this green bar will be the base 1 times the height, but the height is equal to the output at 2, which is 1/4, and so on. So this area will be equal to 1/9, the next area will be equal to 1/16, and so forth. So this green area represents the series. So this is our series, and as you continue going to the right, we're going to get more and more of these green bars, but the total sum will represent the sum of this infinite series. So the series, now that we expressed it as the green area, can be analyzed, like, I guess, visually, and the question of whether it converges or diverges, it's the question of whether this area is finite or not. Now, it is very easy to make the following observation, that the green area is actually less than this red area. So we can see by how the green and red areas were constructed, we can clearly see that the green area is less than the red area. So what does that mean? That means if we can show that the red area is finite, that should convince us that the green area is finite as well. And the question is now, how can we find the red area? So what is the red area equal to? And if it is a finite number, then great. But if it's not, then I guess we'll have to look elsewhere for the proof. Now, the red area, again, it extends a little bit further than the function, than the domain of the function, right? So we can clearly see that the area is made of two parts. It's made of the part that's to the left of the domain of the function, so this part, right, which is equal to 1, plus this part, which is actually the area under the function. And we know from calculus that the area under the function, even possibly infinite area, can be expressed as an integral, and in this case it will be the integral from 1 to infinity, which are the boundaries of that region on the x-axis, and we put the function inside of the integral, just like this. So this expression is what the red area is equal to. And now the only question that we have is, what is this integral equal to? This integral is the improper integral that we have studied earlier in calculus. And to find this integral, we set it up as a limit, as let's use letter t as the upper limit. So we have an integral from 1 to t as t goes to infinity, and we find the antiderivative first. So what's antiderivative of 1 over x squared? It's negative 1 over x. Now we evaluate it from 1 to t, and we have limit as t goes to infinity, negative 1 over t minus negative 1 over 1, and this is equal to the limit as t goes to infinity of negative 1 over t plus 1, and this limit is equal to 1. So this improper integral converges to 1. That means this whole area, so that means this whole integral is equal to 1. So the total area is equal to 1 plus 1, which is 2. So what does that mean? Well, that means that if we consider the sequence of partial sums, then what we just learned is that the sequence of partial sums is less than 2, which means it is bounded. However, since every element of the sequence is positive, so we keep on adding and adding, that means Sn is increasing, which means it is monotone. And we know that bounded monotone sequences converge. So this means that the series that we were analyzing converges, and the green area is actually finite. So the same type of argument can be applied for any continuous positive function that is decreasing under certain conditions. So Later I will summarize it and we will call it the integral test. But before we do that, let's the integral test has two parts. So let's consider another example. So we continue developing the integral test, and this time let's consider the following series, which can be expressed, if we write out first few terms, can be expressed like this. And again, if we try to visualize this series, we'll have to introduce a function. And if we look at the graph of this function, again, it's going to be a decreasing function that looks like this. So it looks very similar to the previous one, but the scale, vertical scale, is a little different here. So even though I draw it very similar, just know that it's just a diagram, right? It's not the exact graph. So the series can be expressed or visualized as the area of this bar, which is 1, plus the area of this bar, which is again 1 over red 2, plus the area of this bar, which is 1 over red 3. Again, how do we find the area? We multiply the base, which is always 1, by the height, which is equal to the output of the function at that point. So this is f of 1, this is f of 2, and so on. And this area can be compared with this area that I'm going to draw in red. And as you can see, this the green area is clearly greater than the red area. So what does that mean? That means if we can show that the red area is infinite, then that should be a convincing argument that the green area is infinite as well. So let's go ahead and try to find the red area. And the red area can be expressed as an integral from 1 to infinity of this function. And this is another improper integral, which we learn how to analyze in calculus class. So to find this integral, or to determine whether it converges or diverges, we're going to introduce a new variable. Then we're going to integrate it while maintaining the limit. And we're going to plug in the limits of integration. And we're going to evaluate the limit. And we have the limit is, as t goes to infinity, square root of infinity is infinity. 2 times infinity is still infinity. Infinity minus 2 is infinity. So what does this mean? That means that this area is infinite. And that means the green area, being larger than the red area geometrically, is also infinite. So what is the conclusion about the original series? This series diverges. And we call this type of analysis the integral test. So we would say this series diverges by the integral test. So in the previous development, we would say this series converges by, so this type of analysis is called the integral test. By the integral test. So what exactly integral test? Let's summarize it. So we're going to summarize it as a theorem, but again, we're going to call this theorem the integral test. And here it is. So if we have a series that satisfies the following conditions. So if you introduce a function on which the elements of the series reside, and if this function satisfies the following three conditions. So the first one is f of x is continuous. The second condition is f of x is positive, or non-negative, I should say. And the third condition that f of x is decreasing. And here I'm going to make this little remark. It doesn't have to be decreasing for all values of x. As a matter of fact, the series can behave as crazy as it wants on some finite interval at the beginning. But as long as it starts decreasing after some finite value of x, then we'll count it as monotone. And if these three conditions are satisfied for this function f of x, on which the element of the sequence reside, then the original series and this integral behave in the same way. So I'm going to use this little squiggle line here to express that they behave similarly. So in this case, what does it mean to behave the same? That means if the integral, this improper integral, converges, then the series also converges. And if this integral diverges, then this series also diverges. And I want to make another remark here. So converges, we know what it converges to. We know what it converges, but we may not know what it converges to. So I'll just say we may not know the limit. So again, this is what we call the integral test. And as you can see from these examples, both functions, both series generated the functions that satisfy all three conditions, and therefore we could apply the integral test. Let's do a couple more examples. Let's consider the following series. And let's analyze the convergence of this series from the very, very beginning. So the question is, does the series converge or diverge? And we're going to start off by trying to recognize whether it's a geometric series or telescoping. And the answer is no for both of them. The next thing we're going to do is we're going to set up the divergence test. So that is, we're going to find the limit as n goes to infinity. And if it's not equal to 0, then the series diverges. In this case, the limit is equal to 0, so the test is inconclusive. Which means that we need to do something else, and that something else will be the integral test. So we're going to introduce a function f of x on this domain, and we're going to check whether it satisfies all the three conditions. So the first one, is it continuous? Yes, it is. Is it always non-negative? Yes, it is, right? So x squared plus 1 is always positive, so its reciprocal is also always positive. And is this function decreasing? If you graph this function, you'll be able to see that the graph of it looks like this. So if you restrict the domain for only values of x that are greater than or equal to 1, you'll see that it is always decreasing. So we're also going to check this. And what does that mean? That means we can run the integral test, and our series will behave exactly the same way as this integral. But this integral is actually, even though it is improper, it's pretty straightforward. So we're going to introduce a new variable for the limit, and at the same time I'm going to find the antiderivative. So it's arctan of x evaluated between 1 and t. So limit as t goes to infinity, arctan t minus arctan 1, and we do know what arctan of 1 is. That's just pi over 4. And finding this limit, we know that arctan has a horizontal asymptote, y equals pi over 2. So that means the limit as t goes to infinity of arctan function is pi over 2. Subtracting pi over 4 gives us pi over 4, which means what? Which means that the integral converges. So that's the conclusion for the improper integral. But by the integral test, that means the series converges. So we always write the conclusion, and we also write the reason. So this one converges by the integral test. All right, let's do another example. Let's do something less trivial. And we're going to start from scratch. So the first thing we're going to do is we're going to ask ourselves, does this look like a geometric or telescoping series? And the answer is no for both of them, for both questions. Next, we're going to set up the divergence test by finding the limit of the nth term as n goes to infinity. And we're going to use the very useful theorem here. So let's go this way. So we don't know if it's going to work until we find that limit. It only works if the limit exists. So here we can use the L'Hopital's rule, and we have the limit as x goes to infinity of the ratio of the derivatives, which is equal to 0. So now it works. We established this equation, and the test is inconclusive. That means we're going to have to advance to the next stage, and we're going to set up the integral test. And to set up the integral test, we're going to introduce this function on this interval. And we're going to verify the three conditions. First, is it continuous? Yes. Second, is it always positive? ln of 2 may not be positive, but again, it doesn't matter what the function does for finitely many first, or what the series does for finitely many first terms. So even though it's not always true, it's almost always true. So we're gonna check this box. And finally, is this decreasing? It may not be decreasing everywhere, but if you graph it, you will see that it will increase from n equals 2. So in terms of the, and we know that from calculus too, like if you have a function like this, whether the integral from 1 to infinity converges or not doesn't depend on what the function does on the on some interval from 1 to some number. It can act as crazy as it can possibly be, and it doesn't affect the convergence in the long run. So again, even though we don't observe this behavior at n equals 1 or x equals 1, we can we can check all these boxes and apply the integral test, which says that this series behaves the same way as this integral. Oops. And we're gonna do this improper integral by introducing a new variable. And here we have integral from 1 to t of ln x over x dx. And it looks like we're gonna have to do some substitution here. So if let's make substitution. Let's introduce some variable, we can call it s. So if s is ln x, then ds will be 1 over x dx, and x will be x will be e to the s, and therefore the limits of integration will be from instead of from 1 to t, it will be from 0 to ln t. And let's continue. So we have a limit as t goes to infinity, integral from 0 to ln t, and we have ln x, which is s ds. So we have 1/2 s squared from 0 to ln t, and the rest is just a matter of carefully writing everything out. So we have 1/2 ln squared t minus 1/2 0 squared, and as t goes to infinity, ln of t is also infinity, squared infinity is infinity, dividing it by 2 doesn't change that, it's infinity. So the final conclusion is that this integral diverges, and the reason why it diverges is by the integral test. So we introduced and went over the first test for convergence, that is called the integral test.